Hello, everyone. My name is Gitika Gorthy, and today I'm very, very honored and excited to be interviewing a very special space champion, Dr. Devon Lundine. Dr. Lundine is a postdoctoral research fellow at the Memorial Sloan Kettering Cancer Center, where he studies DNA repair in the context of space radiation to help protect astronauts and improve radiation therapy for cancer patients. He was the 2023 winner of the Axiom Space Boryung Humans in Space Research Challenge and has participated in NASA STAR and the BioAstra Crew-2. Additionally, he's an adjunct professor at Hunter College, and as a cosmic connector at Imagine Milk, he is building collaborations between space and technology companies to meet their full service production. Previously, Dr. Lundine earned his PhD from the CUNY Graduate Center in Molecular, Cellular, and Development Biology, and he's brought his passion and excitement for sciences and into the space field. And so I'm very excited to learn a little bit more about what drew him into aerospace medicine and kind of the space to Earth verticals he's exploring in the medical field currently. So, welcome, Dr. Lundine. Thank you so much for taking your time to inspire the next generation of aerospace leaders. I'm thrilled to be able to talk to you today and learn a little bit about your work.
Oh my gosh, thank you so much for having me. What a great introduction, and I hope that I am an inspiration. I'm happy to have this conversation. So thanks for the opportunity.
Thank you, and you are definitely. We met at the Empire Space Forum, and I missed your panel in space medicine, but just reading about the work you've been doing has been really exciting. And so I wanted to first start off right there, but about your research related to DNA radiation. And so, can you share a little bit more about your current research and what you're doing with DNA repair, and what got you into this specific research, and where you're currently at with it?
Yeah, sure. So our research at Memorial Sloan Kettering as a institution functionally is working towards eliminating cancers of all kinds for patients. And my background was initially in DNA replication at CUNY, as you mentioned, in breast cancer. And so it was kind of a natural transition for me to come to Memorial Sloan Kettering and continue some of that work. So I transitioned a little bit into DNA repair and really trying to in the radiation oncology world, what we want to do is essentially the fastest explanation is we want to put radiation where we want it in the case of radiation therapy in somebody's tumor. And also we want to keep it away from where we don't want it, which is essentially patients' healthy cells in front of, behind, around the tumor. And in the context of human spaceflight, we don't really want radiation anywhere, or we want to try to limit the damage that it causes. So, yeah, I think that's a very broad overview, but more or less we do kind of particle radiation and very fundamental biology around how DNA is broken by radiation, which is essentially packets of energy that can get deposited in places. And DNA is a biomolecule. It has a physical structure. It has limitations on how much energy you can put into it before that structure breaks. And our cells have an incredible capacity to repair all types of DNA damage. And we're trying to understand kind of the fundamental biology behind how our cells repair different kinds of damage and how cancer can co-opt those pathways and essentially continue to replicate and grow when we would rather those cancer cells die off.
Got it. And I know right now in the aerospace industry, there's a lot of focus on space radiation countermeasures. And is that kind of where do you see because I know you're in a more fundamental space, but do you see kind of the work you're doing adding to the current technology that's out there in terms of protecting astronauts from the different dosages of space radiation we see?
Yeah, so we are, you're right, we are sort of a fundamental biology group, but as part of that, we have some applied research where we're testing several different drugs. So there's a big focus on all kinds of countermeasures, as there should be for radiation. Some of those include kind of physical shielding or materials and trying to explore different ways to protect flight crew or astronauts that are up in orbit or even in airplanes. So one thing I was actually quite surprised to learn is that commercial flight crew, and airliners have a two times higher cancer rate than the rest of the population that doesn't fly, also just from the increased radiation of being higher up in the atmosphere. And our applied work is we're exploring sort of existing pharmaceuticals to be used ideally as a standalone countermeasure or mitigation, but also maybe in combination with these advances in material science and try to explore, is there both a physical shield that you can have from materials, but also a kind of pharmacological countermeasure that can make use of our fundamental biology where we don't need to, or maybe ideally in combination, as I said.
Yes, yeah, that's really like I do think there's a lot of ways we need to target it, and I just think a physical protection is not always the case. And so it's interesting to see how your group is trying to target both. And for those who may not know a lot about space radiation and its impact that it does have in space, could you share a little bit more about, for example, in a short-term flight versus like a long-term flight? I guess, is space radiation a really big concern, or is it more so in the long run when we want to have humans travel further and kind of be out in space for more sustained periods of time? Is that where the space radiation concern really comes in? Or have we seen already astronauts in the ISS facing some sort of negative impacts because of the space radiation?
Yeah, it's a great question. There's a couple of components to that. So the very short answer is we don't know. But the more kind of nuanced answer is that we see there are short-term effects of space flight, and sometimes it's hard to tease out what those effects are from. Sometimes it's from a lack of gravity, sometimes it's the radiation, maybe combinations of factors that are pretty unique to space. And things like SANS, neuroocular syndrome, are more like from the fluid shift. But there were reports from the Apollo astronauts of seeing flashes of light, and those have been kind of drawn back to actually radiation particles ripping through their retina, and they're seeing a flash of light as it tears through the tissue. And so there are some concerns for, and I think similarly, space ISS missions have folks have reported seeing those kinds of things too. And there's all manner of concern about the cardiovascular system being impacted by radiation. So it's kind of interesting because we have these ideas of course, anytime you fly in space, there's essentially hundreds of really dangerous things going on all at the same time. But some of those could be that if you have a cardiac arrest event from induced by anything, but possibly from the radiation in the short term, it's obviously very dangerous and also secondarily puts the ability to complete the mission at risk, which is a problem. But yeah, I think typically we do think of more long-term travel when we think about longer stays on the moon as we try to build out a permanent lunar base or our aspirations to go to Mars someday. In radiation, we talk about three ways to protect yourself, whether you're in radiation from occupational hazard or otherwise. And we say the three things are time, distance, and shielding are the three kind of ways that you can protect yourself. So you want to limit your time, increase your distance from radiation, and hopefully increase your shielding. And so we talked briefly about shielding and hopefully the advances that can be made, although the energies that we see in space make it very difficult to shield all of the radiation. You can limit your time. So, in theory, faster missions are better. So we'd like to be able to get where you want to go, stay there, and get back quickly as much as you can. But as you go to the moon, there's a fixed amount of time you're in space. As you go to Mars, it's, at least 9 months each way. There are longer ways, which you would not like to do to limit your radiation risk. And the distance part is not really possible in space. You can't distance yourself from the radiation source because it's essentially stars that have exploded millions of years ago, or we don't know how or when or where, and there's nothing to slow down these particles that get ejected from these stars in the vacuum of space. And so, we have our ability to travel into deep space so far has been quite limited, and the data we've been able to collect is quite low. So we've had some astronauts in the Apollo program go to the moon, and recently Artemis 2 kind of do a flyby. But that's really been essentially the limit. People are out there for a week, 10 days in deep space. Much longer stays on the International Space Station, but the shielding from the magnetosphere is much higher. So we don't fully understand the biological implications of going somewhere like Mars. And we'd love to know, and we have a sense of the kind of dose that humans will encounter Moon to Mars, et cetera. But it's really an all-encompassing risk anytime you're up there, and it's one of NASA's five red line hazards that they say is it's actually the first one for what's going to limit humanity's ability to continue deep space exploration. And I wish I could name the other four. There, you can Google them, but they're essentially radiation, distance from Earth due to medical concerns, confinement, isolation, um, uh, potentially lack of oxygen, lack of gravity, things of that nature sort of split up into, and maybe I'm missing one or something, but those are essentially the things that NASA has deemed um, must solve issues as we continue to explore.
Wow, I actually didn't know that space radiation was like on top of that list.
Yeah.
Are there, wow, okay. And are there like other big medical related barriers you think we have in terms of like deep space travel? Or do you think space radiation is the really, I know you kind of mentioned a few other factors and how, lack of gravity has an impact, fluid movements have an impact. Is space radiation really, do you think, the most, I mean, it is the most limiting, but are there other ones that kind of are up that scale medically that we need to target and solve?
Yeah, absolutely. I am probably not necessarily the expert in this, but for sure, I think when you think about even most recently on the space station, there was a kind of an undisclosed medical emergency that an astronaut experienced, and they had to come back pretty quickly because there's still the amount of medical care you can do on orbit, whether it's ISS or a moon flight, is extremely limited. You can't do surgery. Even most diagnostic imaging is not realistic at this point. Um, Doing even something like an IV is like
Hard.
that's like not really going to happen. So I think there's a lot of, the unfortunately the weak link in all of our technology and advancements is the human body. And so as we travel and continue to develop these great missions, we have to sort of keep in mind that we're these like really fragile, squishy bags of water that, we're essentially the weak link. And so any medical problem you have is exacerbated by the fact that you are far away. It's going to take multiple days to potentially to get back, depending on where you are, what's going on. And you've got your fellow crew members who are reasonably well medically trained, but there's really only so much that they can do. In the case of many, many, many medical emergencies. Um, I know we'll get into this a little later, but one of the things I worked on actually was looking at the ISS med kit, which is essentially all of the pharmacological drugs that they have on board for the astronauts. And we're working on some interesting research, citizen science research to kind of talk about maybe how radiation can impact those things, or even things like individual genetics, genomics of individual flight crew can affect sort of what medicines will function better or worse in orbit. So all these things we don't know the answer to, and are um, made more complicated by radiation sometimes, and other times it's just simple logistics, like we're just kind of a little far away, far from home.
Yeah, I know. I feel like we focus so much on like the technological barriers we have sometimes, and you see a lot of space companies focused on that. And I think there's very few. I mean, NASA's a leading group in this, but like Axiom as well, I think has done a really good job focusing on the bio aspect. But there's a lot more focus, I think, that needs to come into the medical aspect because
Mm.
I do think, like you're mentioning, there are a lot of barriers that will take a lot of time for us to understand, and humans are individually so diverse that it makes it all the more complicated to figure out the best way the best tools to get humans safely in deep space missions. So, yeah, thank you for sharing that. I feel like I just got so much out of that one little bit. And so, kind of transitioning to the next question, which I think might be related to what you were talking about just now. So, I know you're a part of the BioAstra Crew-2, and I mentioned that in your intro. And I've actually never heard of this program before, but when I was researching about it, I was like, oh, it looks really cool. So could you share a little bit more about BioAstra and kind of your role in this crew and what your experience was like, and kind of who got to get involved in this opportunity?
Yeah, absolutely. So, BioAstra grew out of fundamentally from Chris Mason's lab at Weill Cornell, but also has been an effort spearheaded by Elia Overbay, who's out at the University of Austin, and a couple of other folks as well, Savi Glow and other people that have worked to kind of put this initiative together. And as a participant, I'll do my best to kind of represent them, but they're essentially a nonprofit that's seeking to do many things. But one of the things that I participated in, they put together these crews of researchers of different career stages and have them do essentially what's called citizen science, which is we're coming from all over the world, from all different institutions, and nobody is paying us to do this research, not our institutes, not BioAstra, but we're getting together and saying what data do we have available publicly or through NASA or through this very large data package that Chris and Elia put together called SOMA, which was the Space Omics Medical Atlas, and is essentially a collection of data from several flights, including Inspiration 4, one of the JAXA missions, and perhaps several other missions at this point that have multi-omics, so proteomics, genomics, transcriptomics, all sorts of omics data on as many astronauts as they could gather since this kind of omics era has begun. And what can we glean from this massive treasure trove of information? How can we analyze it in a million different ways to kind of come up with some interesting conclusions? And so one of the things that Crew 2 published with in conjunction with NASA Analysis Working Group, AWG, I think it was the Plant Analysis Working. There are several, all
Yeah,
different
animal
topics.
group. Yeah.
Similarly, you can join kind of, I think, more or less regardless of where you're at in your career and do citizen science like this. We published this article in Nature Microgravity called Feeding the Cosmos, and it looked at the nutritional content of lettuce grown on Tiangong, the Chinese space station. And yeah, it's a really interesting paper. I think essentially I was a very minor character in kind of in putting together that research, but it was awesome to be part of the team and see all the plant biologists really kind of lead the effort there. But essentially, if that was the only thing that you ate, you would have some nutrient deficiencies. And so if we think about long duration space flight and even this nutritional aspect of space medicine, how are we providing food that's resilient to things like radiation or expiration or whatever nutritionally? Or if you're growing food, how does that food grown in orbit differ nutritionally from things that are grown on the ground? So what kind of crops should you grow? What kind of things should you be working to kind of to keep our astronauts healthy in that way as well?
And is this program for those who might be interested in this field, like aerospace medicine wise, or even like the plant biology aspect, do you have to be like a certain level in your career? Because I know you said it was broad and open to kind of all stages, but is there a certain qualification and how long is this kind of this mission sci citizen science program?
Yeah, that is a great question. I was a postdoc when I did it. It
Okay.
was not a requirement to be a postdoc, but I don't remember what the threshold was. If there was a maybe I'm not sure if undergraduates can do it. Possibly, maybe it's more like PhD student
That makes
oriented.
sense.
I'm not totally sure, but there were people on Crew 2 as well that were um, already kind of in their professional career, having done like pharmacy school. So
Oh,
not necessarily even kind of through the traditional academic research track, but yeah, so take a look, double check the requirements. But it was a really great experience. For us, it was a summer, so I think it was about 3 or 4 months. And then, since it's citizen science, you have the option to keep that network together and keep working if you guys want to, really. And they build out essentially BioAstra provides access to a bunch of mentors throughout the process to come in and speak. And we were fortunate enough to talk to Haley Arcano, an astronaut that was a nurse or a nurse practitioner at St. Jude, and herself a pediatric cancer patient. So she came by and talked to all of us, and so there was a little bit of programming like that in the 3 or 4 months while you're kind of working virtually together. And then yeah, a few of us have kind of stayed in touch over the years. And actually, I think Crew 4 applications either just closed or are closing like tomorrow.
I saw that. I saw that actually from Dr. Mason's LinkedIn post. He's like, "Oh, you should apply." I don't know what the exact deadline was, but
Yes, it's basically now. Whenever this comes out is too late.
yeah, yeah. But thank you for sharing about that. I actually wasn't familiar with this program that's so geared towards people who are interested in the space biology. And I know there's a lot of data out there, omics data. NASA Gene Lab has a lot, and you mentioned the working groups. It's open to pretty much anyone. And so there's a community out there that you can really get into this field. And you also were part of an Axiom Space's Humans in Space Research Challenge. And I was also really excited by this because another program I haven't heard of. So I guess what pulled you into it? What was your experience? What did you work on?
Yeah, so early in my postdoc, I knew that I wanted to be working in spaceflight research, and my advisor was very supportive and basically said, "Hey, listen, if you can go get some funding, we'll do whatever you think, whatever you can do." So I had actually worked through a couple of other NASA funded programs. One was NASA STAR, and one is the NASA PI Launchpad, both totally free to participate in, although quite competitive because at least the slots are very limited, and PI Launchpad actually flew us and paid for our hotels and things to be at an in-person workshop for 3 or 4 days. And the focus of some of those efforts were to really build out the explore the challenges and opportunities with what is actually designing a spaceflight experiment look like. And that was really helpful because then when I went to go look for funding, I ran into the Axiom Humans in Space Challenge, which was this kind of joint venture between Axiom Space and Boryung Pharmaceuticals, this group in South Korea that does both private equity funding and kind of pharmaceutical research. And they're a big funder of Axiom Space in the US. Um, so yeah, so they were asking, and I think continue every year more or less. That also changes shape every year, what it looks like exactly. But they're very interested in exploring and funding both startup companies and research opportunities to really make health in space better, healthcare, and just sort of any sort of humans in space, as the name goes. And yeah, it was an interesting opportunity to go. My humans in space, I guess, victory was through Las Vegas. We went to Ascend, is this huge international space conference, and that year it was in Las Vegas, and they said, "Come and we'll get you on stage at a casino, and you get 3 or 4 minutes to try to impress us with your idea, and we'll give you some pilot funding for a project." So yeah, I was very, very fortunate enough to go do that and also meet a lot of really great people and awesome big names in the field and sort of fight back against a little bit of imposter syndrome, feeling like maybe I don't really belong here. I'm with all these people that I've heard of for so long, and to be up on the same stage and um, compete and do well was awesome. Was a great experience.
Wow, yeah, that's really cool. I'm glad there are opportunities like that for you to not only understand what makes a good experiment for someone who's just getting into this field as a young investigator, because I'm sure space mission research is so much more different than like on ground, working with animals. I mean, I think you're about to say something. Is it not so different?
Yeah, no, it is. I
Okay.
was gonna say it is very different in that it just you reminded me the two of the things I found most surprising that we just take for granted when you're designing Earth experiments are one, your ability to move liquid around in tubes is you don't even think about it on Earth, and with no gravity, all of a sudden moving liquid just becomes a total nightmare. So how do you design your experiment in a way that you can maybe avoid that? Or are there ways to engineering solutions to try to figure out like how do I get this done? And the other big thing that I really underestimated or didn't understand was, in every research lab in the world, there are essentially rows of freezers of all different temperatures and lots of devices that can change temperatures and increase them and decrease them at will. And when you design an experiment for ISS, at least, maybe it will be, they probably won't be different for commercial space stations, but maybe it'll be different for commercial space stations. There's really limited ability to store biological material, and the temperatures you can store them at are very limited. And a big part of that is that the space station is just a floating lab, but there's no way to have good ventilation. There's no way to handle hazardous material, toxic material, and anything that can be endangering to the astronauts, like liquid nitrogen, is essentially a no-go. Because if any liquid nitrogen gets out, you have an asphyxiation risk for all the crew members. So and these freezers take up enormous amounts of power. And so all of those kind of combine into like not the most ideal situation for biological experiments where we have access to all this stuff on the ground and all of our protocols and all of our thinking is geared towards a system that all of a sudden does not exist anymore or exists in a very different way. So yeah, there are limitations on sort of what you can do, but in a lot of ways, our creative selves come out when those limitations are in front of you, and that's when you really spaceflight is always interdisciplinary, spaceflight research and spaceflight broadly, and you're always having to engage engineers or other scientists who have tried things to understand like how did you get through these barriers and how did you get this done in a way that maybe we should be doing more of on Earth, but typically we don't really do. You're kind of in your lab and you know how all your stuff works and you've got essentially unlimited power and liquid nitrogen is not a problem and hazardous material, all the stuff we talked about. Yeah, so the quick tangent, but you reminded me absolutely it's different and challenging and
Yeah, thanks for
yeah.
mentioning that though, because I think as you were talking, I was imagining my own experience in the lab and I was like, you're right. I mean, how would I do that? And like, like just we use like a vacuum to like suck out the media, but how do you work with stem cells so easily in space? I know they're doing things in the International Space
Yeah.
Station, but I've never really tried to figure out what tools they're using to be able to do that because I'm like, oh, on Earth it's so easy. Um,
Right.
so
And not to mention, I think I might be getting this number wrong, but essentially an hour of astronaut time and attention is $150,000. So if you need somebody to actually pay attention to do something to your experiment, that needs to be factored into your costs and into your grant structure. And so the more autonomous you can make your experiment, the more realistic it is when you start looking at things like funding too, because their time is so limited that essentially, you really need to focus down into, is there a way for me to do this without any human intervention?
yeah, yeah. I that number did not know that either. That's another really good fun thing to know. I'm
Yeah.
sure like going to these types of like grants and workshops really opens your eyes to like the different considerations you have to make. And so when you are applying and writing out these proposals for NASA funding, or really Trish is a really great funder of
Yep.
space bio research
Absolutely.
or other institutions, like I'm sure these are all considerations that they're looking for. So having kind of that knowledge is so important. So thank you for sharing some of that insight today. And As you were talking, I think it's very evident you're passionate about this field. You talked about your experience at Ascend and how you looked up to so many of the people you ended up sharing a stage with, and I think that was just so beautiful. And so I wanted to hear a little bit about like your journey getting into this space because I think aerospace medicine is somewhat still really niche. So how did you discover this field? What was your aha moment for space or space medicine? And kind of how did you kind of come about to where you are today? I know you kind of gave bits and pieces, but I'm curious about your like kind of origination.
Yeah, yeah, thanks for asking. So I grew up in Orlando, Florida, and I grew up in at the tail end of the space shuttle era. And so from my parents' backyard, I could see when the space shuttle would launch. And when it would come back, your house would shake for a few seconds when the sonic boom, it landed like an airplane. So there was this long tail of a sonic boom that would shake your house. So in a lot of ways, it was unavoidable. You would just sort of say,
You don't
"Oh,
want to think about it, but your house is shaking now
I
because
guess the space shuttle's landing today or now." And for me, it was really beautiful. And I think I remember very clearly the first time I saw a night launch. And it wasn't like today, the space shuttle launched 4 or 5 times a year, maybe. Now you can go in every single day, sometimes twice a day. There are a lot, which is awesome, which is great. But back then it was, the a night launch was like a huge deal. And I remember seeing the shuttle go up, and the sky actually went from black to blue for a few seconds. Like the shuttle was so bright. And then it goes back to black as it kind of fades into the atmosphere. And I was just like, wow, this is crazy. I'd love to be part of this in some way. And I was never really the engineering type. I sort of forgot about it, put it in the back of my mind, went to undergrad and studied microbiology. Um, Never thought I would work my way back into the space sector. Did my PhD in cancer biology, and triple negative breast cancer was what I focused on. And near the tail end of my PhD in 2020, there was this now foundational paper that came out called the NASA Twin Study. And so the fast version is Mark and Scott Kelly are two identical twin astronauts. One was in space for a year, one was on the ground for a year, and Chris Mason and many others, Susan Bailey and many, 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 I think the author list is like 30, 40, 50 people long, worked many labs to collect all sorts of different samples, including looking at DNA damage or immune system dysregulation, or omics, or kind of anything that anyone could see differences between being in space for a year and being on the ground for a year. And this paper came out when I was a grad student, and I just did not, I was just like shocked, and I didn't realize that we could do this kind of work. Um, and so it kind of reignited my thinking, like, not to borrow your
that's
ignited
where it came
thinkers.
from. That literally is where it came from. And I will talk about it after you finish your story. But
Yeah, I was just blown away, and I think it particularly Susan Bailey's work on the twin study, where they looked at chromosomes 1, 2, and 3, and looked at the damage that the radiation caused and the differences in things like telomere length, how many translocations there were, which is a type of DNA damage. And I thought it was amazing. And by the time I got to my postdoc, that particular technology called directional genomic hybridization, a way of kind of visualizing chromosomes and DNA damage, had advanced so that you could look at all 23 pairs of chromosomes, not just chromosome 1, 2, and 3. So immediately the resolution of the data was, about 8 times better. And so that was sort of the starting point for me to say, well, I'd really like to use that technology and do a ground study. I don't think I kind of like skipped over this part, but the actual Humans in Space Challenge project was to test some of these drugs that we thought could reduce DNA damage or reduce the number of cells that could become cancerous. And we used the same technology to essentially to on the ground as best we can mimic space radiation at a particle accelerator, actually at Columbia University in a facility called RARAF. up in Irvington, New York. And yeah, and we're still kind of working to get that project over the finish line. But the short answer is we can essentially see some of these drugs are having a protective effect and kind of mitigating damage from particle accelerator radiation that mimics space radiation as best we can. And hopefully we'd love to get on a space flight and do this kind of work and really prove it in the crucible that is LEO, low Earth orbit. Um, yes, I forgot where the question was. It was just how did
About
I
your
get?
journey. So you discovered that like paper, right, was just
Yes.
like a milestone paper, and you're like, oh, I
Yeah.
can do this type of research. So how did you get your foot
Yeah.
in the door? Like, was it, just kind of going after some, Google searches and figuring out what opportunities exist out there? Or I guess like how did you kind of, once you had that realization, what did you do?
Yeah, I mean, more or less. I mean, I think I was a pretty well trained or I guess well trained um DNA person. And so I thought, like, what are the skills that I have and where exactly is the frontier of the field? And so the twin study was both eye-opening in terms of what can we do, and also this is exactly where the line is for like where the current knowledge is.
Right,
So in the time, in only 3 or 4 years, that technology had developed and further to get better resolution and you could get better data. Um, and using the same technique. And so that was essentially when I looked around at what funding opportunities there were, when I ran into the Humans in Space Challenge, that
right.
was our proposal to
Got
say,
it.
well,
Okay.
we've got a lot of DNA experience. We're at Memorial Sloan Kettering. We've got plenty of skills, whether it's me or the people around us, and we think we could essentially, and we're right across the street from Chris Mason. We think essentially we can, push that frontier forward a little bit, even if it's just on the ground. And so that was really yeah, and essentially it was kind of, more or less Googling or asking around,
Right.
who could fund this or would there be any opportunities? And yeah, it's a combination of like a little bit of luck that the timing worked out, a lot of skill in developing those techniques without knowing that I would be able to do spaceflight, or even without even hoping really that like those skills would be useful, and some creativity around, okay, I have these skills. Is this the moment? Where is the knowledge? Kind of trying to combine all those puzzle pieces to
Right.
put together a compelling story to somebody with funding to say, you know what, yeah, maybe this team, this moment, this question is the right way to go about solving this.
That's awesome. Yeah, and like, kind of similar to what you're talking about Ignited, like that's exactly why when I started Ignited Thinkers, it was from that moment because when I was younger, I never imagined myself as an engineer, which is funny because now I'm graduating with a degree in engineering, but I mean, that wasn't something I
Yeah.
was.
Congratulations, by the way. I
Thank
told you
you.
before the
Thank
call,
you.
but
Thank you. Yeah, it's not like I wanted to be like an aerospace engineer or kind of work on building the actual rockets. I was excited by them, but it was more so I was like a biology. I loved understanding the human body. I wanted to be a physician like on Earth, but also help astronauts or possibly go to space and do research. Like that was always exciting, but I never thought beyond the boxes that I think we're taught in school of
Hmm.
like, oh, this is the one field, second field, third field, and like I think bringing them together was not something I initially thought was possible, similar to your story. And so when I had that moment in middle school and then again in like high school when I discovered aerospace medicine, it really did reignite my passion. And that's kind of where the name did come from when I started the organization. So yeah, it definitely, I think I can relate so much to your story. And I think I want to say all aerospace medicine professionals I've met had a similar story. So I think we're all kind of in this together in this kind of novel field, which has been growing the past few decades really well. And in this journey of yours, did you have any obstacles or challenges you've had to overcome? And like more importantly, how did you overcome them?
no barrier, no obstacles, no.
That's a
No,
first.
yeah, right. No, so many. I think so many that it could maybe be another episode. But I think early on in my science career, I was actually a pretty bad student. So my undergrad career got off like so rocky. I think I failed essentially one class a semester, and I would just sort of juggle which class it would be that I would that not intentionally, but um, and I really struggled to understand how to study, I think. I had like no resistance in like my K through 12 life. And suddenly it was like, oh, this is really hard. And I don't really know how to like handle this pushback or stress or. Um, and I sort of stumbled through and I feel a little bit like I got the chance at redemption and CUNY was very gracious and gave me an opportunity to pursue graduate school at my PhD. And in between I had done some research and work on clinical trials and worked to kind of rehabilitate my image a little bit before I was able to get into graduate school. Um, but that really taught me a lot about resilience and kind of grit and trying to, if something is really important or worth chasing, that there's a cost and a an effort threshold that you have to learn, especially when you're younger, how to push through and how to push yourself and do things that are unusual to you. That continues essentially today, more or less. I think different challenges, whether it's getting grant rejections or fellowship rejections or all sorts of stuff like that is part of or failed experiments. It's all part of the nature of science. And it took me a little bit of time to learn and understand that uh, when my experiments go badly, they are learning opportunities and not like personal failings. And it was really helpful actually to see a lot of scientists I really admired and respected have experiments fail and watch how they responded and try to just sort of like, kind of monkey see, monkey do. Like um how can I mimic these people that I really respect and admire and learn and push through? And even now, I think it's interesting that I think the aerospace medicine field is growing, and even at Sloan Kettering, I think sometimes I get like side eye in the hallway, like I'm the weird space guy. So there's some all my colleagues are great, and I've really loved being at Sloan Kettering. But there is this sense of like a new field is always challenging to especially convince some of the establishment a little bit that like how are you going to overcome these large systemic challenges, no gravity, radiation, all this stuff. Um, but yeah, I think those are all obstacles of the same flavor that like it's hard to do new things, and I would say it's great to do new things. And I always love I put this JFK quote from the moon speech into my dissertation just because I think it's so beautiful and encapsulates the scientific career. He said, "The greater our knowledge increases, the greater our ignorance unfolds." And I think that's true for us as individuals when we try to explore a new career or new skills. You kind of don't know what you don't know. And it's really helpful to have people along the way to try to push you, guide you, console you. Um, as I said, all science and spaceflight research is multi-interdisciplinary, and sometimes that includes like emotional support and getting your mind off of those obstacles and things like that. So yeah, I would say there's nothing worthwhile can be accomplished without struggle and usually enormous struggle, and that's normal. And I think it took me a little bit of time to learn that, being like a young high achiever and sort of struggling with like, well, what's wrong with me? Or like, do I belong here? And I think it's important to realize I more or less, I think everybody has those experiences and that's normal. Like that's just sort of the cost of trying to do something big and bold and new.
Thank you so much for like sharing that. And, I think sometimes it's difficult. I guess now that you've kind of had the moment to reflect and kind of move past it, you're able to share it like with so much confidence. And I think it's really helpful for anyone who's listening now because I don't think, I mean, I'm sure some people find college really easy, but it is a huge struggle. I mean, I personally
Yeah,
coming in from just like a public high school, going into
yeah,
college, it was a huge transition for me because you're suddenly in a school where everyone's super high achieving and you're like, oh, well, now you're no longer the number one student in your like you were in your high school. It wasn't super easy like in high school. And it is a transition, and recognizing your strengths is also important because not everyone's going to be good at the same thing. But thank you for sharing that. And also what you mentioned about aerospace medicine too. I always get like, oh, you're the space girl, right? Like you're the girl
Yeah.
who loves space stuff. And I'm
Which
like,
is not such a bad thing, by the
it
way.
isn't a bad thing. I'm glad to be known as a space girl.
Right.
But like also it's, they're like, oh, is that like really you could do that? Like I didn't know. There's a lot of explanations you have to give all the time, and sometimes you can feel that. And I think it's, when you are doing something new and novel and exciting, you're gonna have different obstacles, but there is a really great community out there, like yourselves. Like every time we meet each other at like these small conventions we have, we realize there's a lot of us, and it's not just, ourselves in like a room. So it is a really growing community and full of passionate people. And I appreciate you sharing kind of your perspective as someone who's living through it or has been through certain moments of, difficulties like that I'm sure many of us share to some capacity.
Yeah, and it's a really welcoming community. I think I found essentially if you have a good idea, that'll take you a long way and people will want to talk to you. A very short time between me being a total space research novice to all of a sudden, last year at the humans or at the the New York Space Week, being on a panel with Chris Mason, the lead of the twin study, and like, how did that happen? Like, I don't know anything about this. So I think it's a very welcoming community. It's a very positive community, and a great idea will take you far.
Yeah, they're not trying to step on each other, but trying to grow together, which I really do feel in the aerospace community. I've not felt like a cutthroat environment in terms of at least the aerospace medicine
Yeah.
community. I'm not sure about other aspects of space. Okay, so now that we were able to learn a little bit about your journey as well as kind of your research, which has been very exciting, my last and final question that I've asked every single person who's done an interview is if you could go back in time and give your younger self a piece of advice, what would that advice be? And it could be related to like life in general, anything career related. It could be anything, just whatever you would want to tell your younger self.
Yeah. It's always hard. I'm sure other people have maybe said this too, because I am who I am because of that younger self. And so, I don't know that I would change anything necessarily, but I think the thing that I've done reasonably well, and if I could tell my younger self to do it more intentionally and increasingly, is continue to find rooms where you are not only not the smartest person, but maybe like below average in that particular room. And don't be afraid to ask questions, and don't be afraid to also advocate for yourself and say, "Hey, I'd really like to learn this thing," and sort of have other people tell you no, or you've got to like grow a little bit more or whatever. Don't be afraid to ask. Um, yeah, I think I tend to be, believe it or not, through this interview, I tend to be on the quieter side, especially when I was younger. And I have always found like that self-advocating part difficult. And you're in spaces where people are intimidating just because they're so advanced, and so you can look on them with awe. So I think like seeing yourself as a relative equal, as a human, and not being afraid to ask, hey, can you help me with this? Can you teach me how to do this? Can you show me this? How did you think about this? Are all things that are hard to do because you feel nervous, like what if they yell at me, or what if they see me as a fool or something. And those concerns are real, but I think the benefits outweigh the potential costs of those things. And you will find um, you learn an enormous amount doing that, and opportunities tend to also open up when you start to self-advocate and just sort of say, hey, I'm here, I'm willing to work hard. I don't know everything, but I'm willing to like learn and just put in hours and time and brain power to help you do what you need to do, and I'll get a ton out of it on as well. Yeah.
I love that. I love that. No, I think that's very true. I also used to be the kid when I was really young in elementary school where I would never raise my hand unless I knew that it was the correct answer. Or
Right.
even if I like had a doubt in my mind, I wouldn't raise it. And then if it was the right answer, I'd be like, oh, I knew that. And I just never said anything, or I wouldn't ask about it because I just wanted to be correct and not wrong. And I think I learned to get out of that mindset and, kind of take no's and take rejections a little bit better, but I think it's something we all need to work on sometimes because a no is never easy and like getting something wrong is never easy, but becoming more comfortable with it and realizing, hey, we all make mistakes, I think is a really good mindset to develop. Though it can be difficult. I don't know if you were going to say something.
Oh yeah, no, I totally agree, and I just think it's we always want to avoid failure, but I think it's one of the inevitabilities of life. It's kind of death and taxes and failed experiments, or
Yeah.
however you want to call it.
Yeah,
And so, well, yeah, whether it's whatever it is, I think take chances. Failure is okay. Failure is not the end of the road. And I've, everyone from athletes to scientists to whoever always seems to say, right, like you can fail 9 million times and still be successful. So I think it's a
exactly.
hard thing to try to overcome, but it's worthwhile.
Definitely. Yeah, it's only one success that's needed and you can like really bolster your career. So, I mean, I definitely agree. You learn a lot from the failures. You go in directions where you might have not otherwise thought to go, and it opens new doors that I'm sure you've experienced and we've all experienced to some capacity. So, thank you so much, Devin, for taking your time to do this interview. I didn't know this much about you before. I just kind of knew a little bit about the work that you were doing in like space radiation with DNA repair. But now to like kind of break down and learn about your story and, kind of what got you into this space. It's just been really nice to get to know your story. And I'm excited to hopefully be colleagues in the future or do something together, and to continue seeing your research grow and flourish. So thank you again for taking your time to do this interview.
Yeah, thanks for having me. And to you or to anyone watching, feel free to reach out, ask questions, do all the stuff that I advocated for, and I'm happy to be part of the community with you.
Thank you.